Welcome, students. We are going to discuss about homogeneous system of differential equation, linear system of differential equation with constant coefficients, and this time we have a complex eigenvalues. Okay. So the idea is we again have x prime t equals to ax. A is a 2 by 2 matrix with the real entries. So real entries. So all entries are real, constant entries. So real constant entries. And we want to solve for x prime t equals to ax. So so if we follow the same way as we did for the real eigenvalues but distinct, we'll see that eigenvalues of this a, since they are complex, they will appear in conjugate pairs. So we have r1 equals to lambda plus mu I. Then the second will be r2, which is lambda minus mu I, where lambda and mu are real and mu is non-zero. The reason why we are insisting on mu non-zero because we want a complex number as we want a complex conjugate pair as a solution or as an eigenvalue. Okay. So now clearly you can see that you can have z1 e to the power. So the solutions are e to the power r1 t z1 vector z1 and x2 t as e to the power r2t z. So this is z1 and this is z2. So these are the solutions. So now since the eigenvalues are distinct, these vectors z1 and z2 are linearly independent, and we'll see that Wronskian of x1t, x2t is going to be e to the power r1 plus r2 of t, determinant of z1 z2, and this is non-zero. The reason why they are non-zero is because the eigenvalues are distinct, then the eigenvectors are linearly independent. All right. So recall eigenvalues or eigenvectors corresponding to distinct eigenvalues. Eigenvectors corresponding to distinct eigenvalues are linearly independent. So as you see, the eigenvalues are complex conjugate pairs. They are distinct because we have the complex part to be non-zero, and hence we have that these eigenvectors are linearly independent, and consequently the Wronskian would be zero. Now what we want is, so we want to now derive two linearly independent solution out of this, right? So note that these entries may not be real. So we want to have a real solutions. So we want to derive real valued solutions though. Okay. So let Z1 be normalized eigenvector corresponding to R1. Yeah, R1 is lambda plus mu I. So now Z1 itself can be written into two parts. So we have real part and we have the complex part. Right? So where A and vector B are vectors with real entries. Okay, so we get A Z1 equals to R1 Z, right? So this is a solution. Now let's take conjugate on throughout. So taking conjugate, this implies if I take A Z1 equals to R1 Z1, if I take conjugate of this, so the conjugate of whole thing, this would imply A. Now A bar is equal to A, right? Since A bar equals to A, and we also have R1 bar equals to R2, right? Because they're complex conjugate pairs, they're conjugates of each other. So R1 bar is R2. This gives me A Z1 bar equals to R2 Z1 bar. So this means that Z2 is the eigenvector corresponding to R2. Okay, so this means the eigenvector corresponding to R2, say called Z2, is Z1 bar, which is going to be A minus IB as a vector. Okay, so this is the setup. So now we want to have real solutions. Okay, so how do we get to the real solutions? We'll take vector U to be half x1 plus x2 and V to be 1 by 2i x1 minus x2. So since by superimposition principle, so superimposition principles or superposition principle implies U and V are also solutions to x prime t equals to ax. So superimposition principle tells us that these are also solutions, and we want to see that these are real solutions. Okay, so let's see why these solutions are real. So what is U? So U is half x1. So what is x1? x1 is e to the power r1 t plus e to the power, so e to the power r1 t z1, which is a plus IB plus e to the power R2t A minus IB. So let's simplify this. So if you take half, so just take A, so whatever is, so we get vector A. What is common in vector A? If we take vector A, we get e to the power, so we get e to the power R1t. So these are not, this is multiple, right? This is not a function. So I should be careful when I'm writing this way. So it's clear that's not function. It's basically R1 times t, okay? So we get e to the power R1 plus e to the power R2 t times A. Then if you take out B common, you get vector B times e to the power R1. So I'll write it down here at the bottom. So it will become e to the power I times e to the power R1 minus e to the power R2 minus e to the power R2 t into vector B. So let's simplify. We see that this will become half. Now, what is e to the power R1 plus e to the power R2? If you look at that, it's going to be e to the power lambda plus mu I t plus e to the power lambda minus mu I t times vector A plus e to the power lambda plus mu I. So e to the power mu t plus e to the power, sorry, minus e to the power lambda minus mu t times vector B. Okay, so now we need to simplify this further. So notice the following. In this, I can take half. If I take e to the power lambda t common, what is left? E to the power mu I t plus e to the power minus mu I t. A, same here as well, e to the power lambda t times I, what is left in bracket, e to the power mu I t minus e to the power mu I t, okay, times b. Now, what is e to the power mu I t plus e to the power? So note that e to the power mu I t plus e to the power minus mu I t is going to be, so first of all, let's expand this. So this is going to be cos of mu t plus I sine mu t and plus e to the power. So the second part is going to be e cos of mu IT minus I sine of mu t, cos of mu t minus I sine mu of t. Now these guys will cancel off, right? So u, and similarly for the other part, so u will simplify to e to the power lambda t common divided by 2. So here you will get cos of mu t times a, and for the other part you will get I, you will get 2 sine of mu t times I b. And then you have 2 and 2. So this 2 and these 2 will cancel. So you're left with e to the power lambda t cos of mu t a times vector a minus sine of mu t times vector b. So this is your u. Similarly, similar work can show that v is going to be e to the power lambda t sine of mu t a plus cos of mu t vector b. So these are u and v. Okay. So now we want to show that these sets are fundamental sets. So how would you show that? So the way to show that these sets are fundamental is let X be any solution. So there are two ways to show that. So either, so how do you show that these two form a fundamental set? So either show that U and V, so Wronskian, compute the Wronskian of U and V and show that it's non-zero. Or notice the following, or observe. So observe that X equals to U plus IV, and X2, your solution is U minus IV. So if X is any solution, any arbitrary solution, that can be written as a linear combination of X1 because these solutions are fundamental. And on the other hand, that can be written as C1 plus C2 of U plus I sine C1 minus C2 of V. So call this as C1 prime C2 prime. So this is can be written as C1 prime U plus C2 prime V. So you see that hence every solution can be written hence any solution X of t can be written as linear combination of U and V therefore UV are or is a fundamental set, is fundamental. Now the upshot of this is, so what was this discussion about? So we had U and V, so we had X1, X2 as complex solutions and we converted them into real solutions. I mean, we found out a corresponding real solutions, which is going to be U and V. So vector U and vector V are fundamental, is a fundamental set. So let me basically go through the summary of it. So for 2 by 2 matrix A, with complex pairs of eigenvalues lambda plus or minus I mu, with A plus or minus IB as corresponding eigenvectors, the, the real valued solution form a fundamental set and are given by the following. So let's deal with an example. So consider the following system. Here your A is this guy. So first step, step one. So steps. So first step is to find eigenvalues. So find eigenvalues. That means you find A minus Ri, determinant of this equals to 0. This implies determinant of minus R, 2 minus R minus 5, 1 equals to 0, which is, so this determinant is R squared minus 2R plus 5, right? Now, how do I solve this? I mean, I can use quadratic formula, or otherwise you can see that R is equal to 1 plus or minus 2I. In this case, lambda equals to 1 and mu equals to 2. We are comparing it with what? U lambda plus or minus mu I. Okay, so we got this. So now we need to find out A and B, right? So we need to find vector A and vector B. So now we have, so to find A and B, so we have A minus 1 plus 2I of Z, vector Z equals to 0. So that is same as solving for, this implies we are solving for minus 1 minus 2I minus 5, 1, 1 minus 2I, Z1, Z2 equals to 0, 0. Note your Z1, Z note, your vector Z is actually given by two components, Z1 and Z2. Okay, so this is a notation. So we'll see that right away we'll get 1 minus 1 plus 2I Z1 plus Z2 equals to 0. And we get minus 5 Z1 plus 1 minus 2I Z2 equals to 0. Now note that this second equation is a multiple. So second equation is a multiple of first. Why is that? Notice that 1 plus 2I times 1 minus 2I equals to 5, right? So you see, if I multiply this equation, the first equation, if I multiply this equation by 1 minus 2I, I will get 1 minus 2I for the sixth part, and then I'll get 1 minus 2I, so I'll get minus 5 there, right? So the first one is a multiple of the second one, or vice versa. So we only need to find out for the first case. So we have Z is then, my Z is going to be, so the first coordinate I can take 1. If I take Z to be 1, what do I get Z2? Z2 is 1 plus 2I times Z. So this is what I get. And then this can be written as 1, 1 for the real part, and the complex part will be 0 to I. So I get what? A, this is my A, this is my vector B. So now we can write down the solution. So U is going to be e to the power lambda t cos of mu t A minus sine of mu t B, which is going to be, what is my e to the power lambda t? Lambda turned out to be 1, as you can see here. So lambda is 1. So if I write that down, I get e to the power t cos of mu t, which is cos of mu is 2, right? So I get cos of 2t times A, which is 1, 1, minus sine of 2t B, which is what? 0, 2. Yeah. And if you want to simplify that further, that is going to be e to the power t cos 2t times cos of 2t minus 2 sine of 2t. Yeah. And you can see that all the entries are real. So this is a real solution. And similarly, we can show that v equals to e to the power t sine of 2t sine of 2t plus 2 cos 2t. Okay, so this can be done by the similar computation. So what is my general solution? My solution is going to be x equals to c1u plus c2u v, my bad, c1u times c2v, which is going to be c1 e to the power t, first one, which is cos 2t cos of 2t minus 2 sine 2t plus c2 e to the power t sine of 2t sine of 2t plus 2 cos of 2t, where your t, c1 and c2 belong to are arbitrary constants. Okay, and they will be determined by what? They'll be determined by the initial value, if the initial value was given here. So now look at the direction field. So this is how the direction field looks like. So in this case, as you can see, so here is the equilibrium, right? Ax equals to 0. Since the determinant of this is non-zero, the equilibrium is, so x prime equals to 0 implies Ax equals to 0, which implies x equals to 0, right? So if determinant of A is not 0, then the equilibrium is going to be x equals to 0. So as you can see, the solutions are spiraling away from, the equilibrium x equals to 0. So all solutions, you can see all solutions spiral outward from the equilibrium x equals to 0. Hence, so for this reason, we call the equilibrium as an unstable, so we call it unstable spiral point. Now, if you look at this, actually it is, the reason for that is you have e to the power t, which keeps on increasing. So that's why it's going away. So now if you have a solution where e will have a negative power, then the spiraling will happen inwards. Okay, so let's have a few more discussion about this. Yeah, so why does it spirals away? The one, so two, equilibrium is unstable is unstable because of this e to the power t, right? It has a positive power. So it's unstable because the real part of eigenvalue is lambda equals to 1, which is positive. Is positive in this case. If it was negative, then the story will be completely different. Then it will spiral inward, right? It's positive in this case. So now let's attend the following system. In this case, when you work it out, the eigenvalues are r equals to 1 plus or minus I with a minus sign. You can work it out. So this is going to be this. And the equilibrium again. So you can see that determinant of this is non-zero, and its equilibrium is an asymptotically stable spiral point. Stable spiral point. Again, stable spiral point. And the reason for that is that the eigenvalues have the real part as negative. So you'll see that this is your equilibrium solution, and solutions are spiraling into the equilibrium, right? So the solutions are spiraling in. So this is the story. Now let's look at another example. Example 3. So find the general solution of the system, this, and we'll plot the, so, and then we'll look at direction field and phase portrait. So again, here A is 0, 2, minus 1, 0. If you solve, you'll get eigenvalues are r equals to plus or minus 2i, square root of 2i. Now note that there's no real part, all right? So in this case, you can show that eigenvector corresponding to r equals to square root of 2i is z equals to square root of 2 minus I, which can be square root 2, 0, which is your A, plus IB, and your B is basically 0 minus 1. This is your B. Okay. So you can deduce the solutions are going to be U equals to square root of 2 cos root 2t and sine of root 2t, and V is going to be square root of 2 sine of square root of 2t and cos of square root of 2t. Yeah, so this can be this will easily follow from the same computation which we did here. Okay, so just writing down the computation now. Now let's notice in this case what happens. In this case, the trajectories are closed. So you see the trajectories are closed elliptic curves. So the solutions are closed elliptical curves, not elliptic curves, my bad. Elliptic curves are something else. Yeah, they are cubic curves, okay, over different kinds of fields, but we are discussing elliptical curves here. Okay, so elliptical curves are the curves which are form of ellipse. So they are closed elliptic curves. We call the equilibrium in this case as center. Equilibrium x equals to 0. So 0 as a vector 0, a center. It is stable, but not asymptotically stable, right? It is stable, but not asymptotically stable. So let's have the summary of discussions. So for x prime equals to ax with a non-singular matrix A that has complex conjugate pair of eigenvalues, there are three cases possible. You look at the eigenvalue, which is r equals to lambda plus mu I, or plus or minus mu I. Depending on this part, the real part, the behavior is determined. If lambda is greater than 0, then x vector x equals to 0 vector becomes an unstable spiral point, as we saw in the first case. So this is unstable spiral point because your lambda was 1 in this case. In this case, lambda was negative. So if lambda is less than 0, x equals to 0 vector is an asymptotically stable spiral point. Yeah, you can see that there is a convergence happening to all the converging to 0. However, if lambda equals to 0, then we get a stable center, all right? But it's not converging to the equilibrium, all right? It's moving in the circles. So we have a stable center, right? Thank you very much for your attention.